So as you all know, the session, the panel discussion right now is, how much data for training models and how much data do you really need. So I'm joined here with my esteemed colleagues. We'll start from here. Lucas, he's a co-founder of Protein Cure. So Lucas, could you do a quick 30-second intro for yourself?
Sure. Protein Cure is a startup based in Toronto, Canada. We work on the design of protein-based therapeutics. You can think of things like insulin. We build computational tools, and we use computational tools relevant to this discussion. Humanity basically knows no protein structures in terms of what's possible, so it's a problem. You're constantly constrained by your lack of data.
Thank you, Lucas. With that, I'm going to move on to Raj. So Raj, he's the VP of Interaction and Analytics Laboratory at PARC. So Raj, could you give a quick 30-second intro of your company?
Sure. So Palo Alto Research Center at PARC is the birthplace of computing, personal computer, Ethernet, printing. And so these days we do a lot of research, AI being one of those things that we have continued to do since the 70s, and I lead the AI research lab.
Thank you, Raj. With that, Karen is the lab director for SRI International AI Center.
Hi, I might take a little bit of exception with Raj's comment because SRI likes to claim that personal computing was actually invented there with Doug Engelbart's work on the mouse and interactive machines. But of course, PARC did take that technology and really make it sing. So maybe it's a collaborative effort. But for those of you who don't know us, SRI, former Stanford Research Institute, we're an independent, not-for-profit research organization in Menlo Park, California. We do work across all the sciences, engineering, education. I run the AI lab, where we do work essentially across the whole spectrum of different kinds of AI concepts. So.
Thank you, Karen. So we all know we've talked in the last time, half an hour or so, and even for the last couple of days here at the event, that data is foundational to AI. We really need, especially the neural networks of deep learning models, they need huge quantities of data. So my first question here for the panel here is that, is big data a must for training AI models? And if yes, what are the tips and tricks to support the big data requirements? So how about Raj, can you take a pass at it?
Sure. So as Dr. Shin talked about it, right? So the algorithms require a lot of data, but not all data needs to be annotated by experts and available in a labeled way. He talked about it in context of healthcare, where there isn't necessarily a well-understood mechanism about how tumors grow and things like that. But there's a lot of stuff in the world where we understand the laws much better. So laws of physics are much better understood, laws of chemistry are much better understood. So we can use those laws to augment the data to reduce the requirement for annotation and labeling and things like that. So a very simple example would be if we understand the laws of physics, well enough to know that if something is revolving, so for example your tires or clutch, they're going to behave in specific well-understood ways, right? Things that are sort of sliding against each other in a rotational way are going to stick, are going to wear down. And so if you understand the physics of their operation, you can use that to create a lot of synthetic data that you can use to understand how they will behave, how the parts will fail. So where those laws of nature can be used, we can use that in a very sort of systematic way to augment these things.
Awesome. Thank you, Raj. So Karen, if I may ask you, what are the top reasons, for reducing the amount of data that is required? Apart from that, there are ways and tips and tricks to kind of create that via synthetic method. But could you talk a little bit about, what are the reasons and how do you kind of look of the role of humans in this particular decision making?
Sure, I'd be happy to. So we heard in the previous talk, right, oftentimes you just don't have the data, or it could be very expensive to get it if you have to pay humans to go in and label examples to drive the learning capabilities in your system. Even if you do have the data, though, there are some good reasons to try to want to not use it all. So there was a really interesting paper that came out of the University of Massachusetts at Amherst a few months back that was looking at the cost of running modern deep learning architectures and the sort of state-of-the-art transformer capability on the kind of state-of-the-art natural language understanding models that were generated. They did an estimate based on the published description of how those models were created, where they said that and their estimate it cost $1 to $3 million of compute time to generate that model because they were running over so much data. They had over 200 million parameters in their model. So, that's not sustainable if you think about the carbon footprint of having done that. That's certainly something that we as a field would like to move away from. Really starting to try to look at techniques where we can reduce the amount of data that's necessary without sacrificing the quality of the models that we generate.
Awesome, thank you, Karen. So Lucas, if I may come to you, we all talked about synthetic data and ways of kind of doing that. Could you talk to us a little bit about some of the scenarios and the tips, trade-offs of quality and amount of data that you need?
Sure. So I think for all of us, when we're generating synthetic data, there's always that trade-off between quality and amount. Usually, so for example, if you're simulating, which is a really common way to augment your data, a more accurate simulation, whether it's physics-based or really any other method that just requires more compute, simulating more often is better. So doing many repeats can give you higher quality synthetic examples, but again, it takes time, it takes money. So that's really the trade-off, is starting to understand, based on your use case, do you want a lot of examples where there's a little bit of noise and the synthetic examples aren't as great? Or are you better served by having fewer examples where you're really confident that these represent kind of a good ground truth synthetic case?
Awesome, Lucas. Could you talk through a couple of examples within your own initiative and project as to how you went about it?
Yeah, sure. So, if you're talking about working with small data sets, and as Raj mentioned, not every problem can be solved with small data, but usually there's a couple of ways to try to work around it. In our case, we do a lot of data augmentation, so creating synthetic examples with simulations. We simulate the atomistic kind of behavior of a protein and its interaction with the target, and that kind of creates a little movie that can be the underlying data. So instead of using an experimental result, you're simulating that experimental data point and trying to use that to train your examples. Similarly, you might try to think about incorporating, and this is a little bit more of an art, the actual laws of physics into your model somehow. That can be very naively by constraining certain functions or by constraining certain things, but there are kind of other more sophisticated ways also to leverage the fact that you do know some of the thing about chemistry and biology when you're trying to predict, how does this molecule fold or how does it interact with some other molecule.
Awesome, pretty interesting. So Raj, I remember when I was chatting with you, and in his case, in your situation, there's a very interesting use case where you have lots and lots of data, but what is the meaningful data that you're actually going to use? Could you elaborate a little bit on share with the audience here?
Sure. So this is not uncommon, especially in physical sciences, right? So when you create systems that are meant to last a long time, think of a turbine, think of any kind of large capital equipment, expense kind of thing, big cranes, whatever the case might be, you design them to be very reliable, right? And so what that means is that the data you get about them when they're operating is of normal operation. But what you really care about is when they fail. So when you fail, you want to be able to detect the failure, diagnose the failure, and if possible, predict the failure before it happens. But you have all your data about normal operation, right? And so the data that you have is not the right kind of data for diagnosis. It may be sufficient to say, is it deviating from normal to detect a problem, but for diagnosis, for prediction of problem, that typically is not sufficient. And so what we try to do is, again, sort of use these kind of laws of physics to build models of operations of these things. So in case of a wind turbine, we understand sort of the rotational motions, how the physics works. So using the data from the normal operation, you can estimate the parameters of the system, and then you can use laws of physics to extrapolate out to say how will this thing degrade over time. So because these are based on laws of physics, you can do that extrapolation, which is not possible to do in machine learning models where it's much more about interpolation, sort of predicting how a curve fits rather than saying how the curve extends beyond the data you've seen. And by relying on the laws of nature, sort of creating the right data so that you can do the task.
Awesome. Karen, how about you? Could you shed some light in terms of certain examples where synthetic data and is used and how you kind of take care of the quality and quantity of the data?
Sure, I'm actually going to go in a slightly different direction, which is that we're pursuing a line of research in my lab where instead of trying to generate, I mean, we do some generation of synthetic data, but we've heard a lot about that. So another approach that we're taking is trying to build hybrid learning systems that combine sort of the old-fashioned AI, the rule-based symbolic kinds of models, directly with the underlying neural architectures, and doing this in a unified way where you can have kind of bidirectional flow of information. The learned models are used to sort of soften the interpretation of the logical statements, and the logical statements are used to drive the learning process. So it's a really interesting model where you get this bidirectional flow of influence going from the logical representations up and down through with the data. And this is something that I think is really important because we have experts that have a lot of knowledge in particular domains, and there's no reason to try to learn everything tabula rasa just from the data. I mean, it's a lot more sense that if we've got expertise, we've got the models, as we were talking about with some of the other panels, we should build that into our learning architecture rather than trying to rediscover those things that we already know. And we in particular have been trying to apply this architecture to various kinds of design tasks. So here it's not laws of physics that we're trying to build in, but it's really sort of heuristics or expertise that a domain expert might have. They've got some intuitions about this is the right way to solve this problem, and we fold that into the learning models.
Can I build on that?
Yeah, sure.
I think what Karen mentioned is a very, very important point because we assume when we build these machine learning models that we don't know anything, and everything has to be learned from the data. But we do know a lot, right? And so, in her case, as she's talking about sort of doing this hybrid thing with logic, a logical framework, we do something similar. But so, for example, we had a task where you had to do retinal segmentation from an image of a fundus of the eye. But we know something about the structure of the vessels. We know they're long, cylindrical, continuous, right? You can't get the stopgap kind of vessels. So by using these notions of continuity, geometry, you can impose that on top into your learning framework. So it requires much less data and is more robust in its prediction.
Yeah, awesome. So Lucas, if I may ask you, what are the advancements that are happening? Most of the training that we have heard so far is like supervised learning, right? So what are the different training methods that are kind of being evolved into, and how is that going to be migrated more towards unsupervised learning, where small data models, smaller sets of data, less data volume can be used? Your thoughts and perspective on that?
Yeah, I mean, there's definitely different things happening right now. So kind of really hot a little while ago has been reinforcement learning with simulations, which is kind of a lot of what we've talked about. To kind of some of the other points, there are kind of advances in architecture designed specifically for classification problems. So, it's kind of exploding literally in the last 18 months is kind of the notion of few-shot learning, trying to basically learn from a very few amount of examples and learn from a similar kind of training set. And of course, there's kind of the notion of transfer learning, which similarly is kind of not necessarily designed for small data problems, but you might hope would also be applicable in that world where you take a model that is trained somewhere where maybe data is more ubiquitous, and you're able to adapt for your current situation. And so these are all kind of, I think, things people are trying, as well as maybe the least technical method of just being better at feature engineering. And it's kind of one of those places where domain expertise actually matters a lot more than machine learning, but everyone, I think, is still figuring out what's the right combination of these novel techniques or ideas to best suit their applied use case.
Awesome, thank you. Karen, your perspective on that? Where are you seeing things evolving?
Yeah, I completely second the comments. I think there's a lot of really exciting work that's going on and very much at the research frontier right now and thinking about transfer learning and also this concept of learning how to learn, which is another way of being able to transfer from one domain to another. So you've learned a skill in one environment. How do you develop the mechanisms of self-awareness such that you can abstract from the specifics of what you learned in one domain to expedite a faster learning process in the new domain? And right now the work there is still kind of early days, but it's really exciting to see some of the results that are coming in.
Yeah, that's great because we're talking about the cutting edge research 1 to 3 years from now, so,
Yeah.
or maybe even beyond that, right? So that's great. Raj, your perspective on that? What do you see?
Yeah, there's a lot of excitement in this idea of semi-supervised learning where you have a lot of data, most of that is unlabeled in some way, and you have a much smaller subset of data that is labeled. So the example that Dr. Shin gave was synthetic generation of Jennifer Aniston's different kind of faces and things like that. So in context of that, you can imagine you learn from unlabeled data not what Jennifer Aniston looks like, but what a face looks like, right? You have 2 eyes, a nose, so what is the structure of a face? And then from a very few images, you learn, okay, now, this is hair, this is sunglasses, these are. So you learn the sort of the basic structure from a lot, and then generalize with small amounts of data. But the other thing is, there's a lot of learning that's already been done, right? So Karen mentioned sort of the cost of learning, millions of dollars and thousands of hours. Can you build on top of those things, right? So that, again, sort of saying, we know what this task that we learned was about, and how close is it to the thing we are doing. So there's something that DARPA is doing now, the program, they have a program called Learning with Less Labels, where their aim is to reduce the requirement of labeled data, which is the sort of the costly part of this, by 6 orders of magnitude, right? So if they're anywhere successful in that, that also will help by using these kind of things.
Awesome, thank you. So before we open up for questions, we wanted, when we discussed it together as a team, we felt that we'll open up more time for Q&A because we're always running short of time. But before I do that, I want to ask, just for the fun of it, if people ask me, which is like kind of a funny question here, people say, is it like petabytes of data? Is it terabytes of data? Is it like exabytes, exabytes? What is the size of the data? It's hilarious, right? Because there's no such thing. Do we need millions, 15 millions, 30 million images to train a deep neural network? Any just fun answers, just for the fun of it.
So, obviously, no matter what rule of thumb I say, I'm going to be immediately wrong. But, I think the one thing to just really keep in mind is you need big data when you have a ton of features, right? So whatever you're studying, like an image is the classic example where there's just a ton of little dots that basically are all features, or when the relationship you're trying to understand is really hard to understand. So the example of brain tumors is perfect. If either of those things starts to be less and less true, that's when you can get less and less data. So it's not a matter of petabytes or maybe that kind of measure, but you can start to use, if you only have, say, 10 or 20 features, okay, then maybe 1,000 samples might be enough, assuming that the relationships are pretty simple. But if the relationships are very nonlinear, if there's tons of substitution effects and complementarities, then 1,000 might not be good enough. And so it's just kind of, I think those are the 2 real levers you have at your disposal. And so thinking about that and trying to work within that is really all you can do. But certainly in a practical sense, I think we've seen really simple neural network architectures do reasonably well with 1,000 data points. They're not fancy, but they're kind of competitive and better than other machine learning methods if you have kind of the right problem type.
Great, thank you. Yes.
So maybe I'll cheat a little. I'll say you need as much unlabeled data as you can, but we've been able to get away with using as few as 10 to 20 labeled data points by using them.
Yeah, Karen.
It all depends. I mean,
I know. I wanted to put
really
you guys in
depends
a
on
tough
the problem
spot.
that you're trying to solve. And again, I think with some of the new techniques coming out, the current kind of almost insatiable need for data, I think we can get past that as a community. We can start to come up with techniques where we understand how much data we need for the problem at hand, and we can limit compared to what we have to do today.
Yeah, so again, bottom line, the answer is it's all subject to your specific use case.
That's
and your
right.
techniques that you're using, the data points, kind of relate to that. Any key takeaways that you would like to share with the team here today? Anyone can go start. Karen, how about you?
There's a lot of exciting work going on in this space right now. I would definitely say stay tuned. I think you're going to see some significant advances over the next couple of years in terms of whole new families of technique that reduce the requirements for data. In particular, if we can build on having ways to pull in human experiential knowledge rather than trying to discover everything from the raw data itself.
What I'll say is that machine learning is very rapidly moving from requiring experts to becoming very commonplace, and so there's a lot out there and there's a lot coming that should enable anybody who's interested in being able to take off-the-shelf things and use them for their tasks, and so just build on top of what others have already discovered.
And maybe I'll take a slightly different take, because I come from maybe a bit more of an applied setting, and I've kind of worked in healthcare and finance now, and I think the question for those of you who are trying to do applied problems is, how do you best incorporate domain expertise? And Karen so talked about one way, which is kind of thinking about the heuristics that an expert uses and trying to incorporate that into your model. The other way that's really common is, again, a similar idea, but like using it up front in the feature engineering and saying, what are we going to feed in as an input? And what I've found is that if you do both, you start to get the biases of a human. And so the question is, what's the best way to leverage that domain expertise, which is going to be extremely valuable to those of you who are in a company that is not just using machine learning, but is good at something else, whether that's finance, healthcare. And I think that's really what set people apart, and it's as much art maybe as it is science. And so it's one thing that I would really think about as you're going forward is where is the best place to use that domain expertise, because it is valuable, but using it everywhere, you start to just go back to might as well have the person do it themselves.
Thank you, Lucas. So if I may just say one thing, we always kind of say, people who have been in the industry for some time, you all remember the age of data warehousing and business intelligence hype, and every project failed. So always start with a measurable ROI. Think about the business case first, and of course technology is integral to it, they go hand in hand. So try to kind of work through that process first. Start small, it's okay to fail. As per IDC, we do research, and more than 51% of the projects we surveyed, about 2,700 organizations worldwide, and they all reported that only 15 to 17% go in to see the light of the day, and most of them fail. So it's not to be ashamed of. If it fails, it's okay. I showed those stats to some of the folks recently at an event, and they were like, oh, I feel so much better now. So, but having said that, it's costly, it's time consuming, it's hard. You really need to kind of fail fast, learn from your experiments, and strive to thrive. So with that, I'm going to open up to questions. Can we have a mic for her, please?
Hi, so I have a question about generating synthetic data. So sometimes the problems I'm dealing with within healthcare, we just don't have enough data to train specific models for. And I'm running into several people at the conference who advise me, oh, maybe have you ever thought about doing making synthetic data, which I'm not very familiar with the process of. Or can you talk about best practices for making sure your synthetic data still mirrors your training data? How do you go about measuring that the deformations, the transformations you make aren't deviating too much from your original data?
Sure. Actually, the previous presentation gave the kind of the right answer, which is you generate some synthetic data, and then you train a model on it, and you train it on the real thing, and you see whether your model is just as good, right? So there's some, I'm looking a little bit technical here, there's some test set that's ground truth data, and you get some training data that's real, and some training data that's synthetic, and you train your model on both, and you test it on kind of the same out-of-sample test set, and that's kind of the generally accepted way to figure it out. In healthcare, again, it really depends. Synthetic data is kind of a broad category. There's the fanciest kind, which is kind of GANs, and then there's kind of simpler kinds, which might be simulations or other tools, which you don't necessarily need to, they're generating data through some other process. And so if you're doing it without some other process, there's other tests you can run to make sure you're kind of obeying the laws that process is supposed to be obeying. But in my experience, at least in the healthcare space, that's generally, or the life sciences space, that's how we would do it.
We've also used surveys with experts, right? You generate them, you then put them in front of experts to see if they can distinguish between what you have generated. So the idea of GAN would put a person in the loop.
Yeah, and I've seen some work, people looking at things like trying to recognize different kinds of products in your local grocery store. They're coming down the conveyor belt, being able to identify things. So that's an example of something where it'd be expensive to get data of the different products in all different kinds of orientations and with different levels of occlusion from other products and things, but you can easily generate those, right? Once you've got some examples, you can just sort of move things around in the images so that you're creating lots and lots more examples from the data. So I think some of it too really depends on the nature of the problem that you're looking at and whether you could easily implement some capabilities that could generate a lot of additional examples for you in that domain space.
see that this AI technology is spreading to so many aspects of life, especially when there is a lot of money gets involved. And then we see that robots playing music and then drawing, not quite drawing, but making sentences and then poets and poems and even novels. Then we see that the robot helping kids to learn, so we see that's about focused kind of learning. But I wonder whether you have seen any AI technique that is helping kids to paint something or draw something. So, that's my question.
Whether those things exist?
Yeah.
I think the answer is yes. Many. I mean, so if maybe we can talk offline the kinds of things you're looking at, I'm sure people here can suggest.
Because I have a point, and one girl is very, she's almost genius in drawing. But my boy is almost nothing in drawing. And then my girl is teaching my boy how to draw, but it's really, really hard for him to learn and then do any kind of meaningful drawing. And then I was thinking about if there is some kind of AI technique even helping my boy who has nothing, no talent in drawing. I thought it would be pretty cool.
Or perhaps I could use one of the AI tools to generate some real good craft artwork. I just, yeah, any question?
No, it's not a question. I just wanted to bring up a joke in terms of how many data we need. We used to joke we need gazillion. So there's no such word. It's just a buzzword. We need gazillion.
It's a slang that we all use. With that, I'd like to thank the esteemed panel here. Thank you so much for your time. Hope you guys found the the discussion here useful. If you have any other follow-up questions, I'm assuming some of them will still be here. So we'll be here, and please reach out to us. Thank you so much.